All right, so welcome to the screencast for Nuclear Chem objective number 6. This objective, it will take us basically 2 days in class to get through all the stuff we have to do, and I'll explain that as we go along and on the explanation sheets I have at the end of this unit, or the end of this objective. So objective number 6, we're going to calculate and graph the amount of remaining product after radioactive reactions occur using the known half-life of radioactive isotopes. We're going to use this lovely equation, which I know looks complicated, but it's really quite easy to use. So our essential question is, how is half-life of isotopes determined? Half-life shouldn't be new to you. This is a concept you should cover in biology as well as chemistry. We are going to watch this particular video in class together, so don't worry about watching that. But the definition of radioactive half-life is the time it takes for half of a radioactive sample to decay. So if I had 10 grams of something, how long would it take it to decay to 5 grams? So just half of the sample. There are some examples that I've given you here of known common radioactive isotopes. Carbon-14, that's the one that you generally see us using for carbon dating of living organisms. It takes 5,730 years for carbon-14 to cut in half. Radon-222 is about 3.8 days, and it goes through alpha decay. I've told you the type of decay that it goes through, whereas carbon-14 goes through beta as well as giving off gamma. Uranium-235, 7.0 times 10 to the 8th years. So add 8 more zeros to that. That's how long it takes for a sample to decay. So if I had 5 grams, for it to decay to 2.5 grams, it would take 7.0 times 10 to the 8th years. That's a long time. And uranium-238, which is what we generally use at nuclear power plants, 4.46 times 10 to the 9th years. And it goes through alpha decay, whereas uranium-235, those particular isotopes go through alpha and gamma decay. But just a little bit on some, radioactive isotopes. Every isotope has a different amount of time that it takes for it to decay. The equation that we use here, this is going to be very useful to you. The different variables in the equation all mean different things. So A is going to be the amount left. So that's what you're going to calculate. Generally, it's going to ask you, or it's going to give you all these other variables, and you just have to calculate after a certain amount of time how much remains. So your AO or A0 is going to be your original amount. You're going to take your original amount times 1/2 the total time divided by the half-life, so to that power. So 1/2 to the power of time divided by half-life. Time divided by half-lives equals the number of half-lives. So it's actually really easy to use this equation, you're going to see. I've just worked through or given you a little explanation. We can work out this together again on the board tomorrow or in class, and that's no big deal. You have 100 grams of radioactive carbon-14, and we know the half-life of carbon-14 is 5,730 years. So if I had 100 grams, how long would it take it to get to 50? So how many grams? You could think of it in terms of that. How long would it take it to get to 50 grams? Well, it would have to go through one half-life, which is 5,730 years. Another way to ask that question would be, how many grams are left over after one half-life? So you're actually solving for A here, the amount that's left. So if you plug everything into that equation, you end up with 100 grams, which is your original starting amount, 1/2 to the first power. The total time divided by the number of half-lives. Well, 5,730 years is going to be your total time because you have one half-life, divided by the number of half-lives, which is 1 here, 5,730 years. So you get 50 grams being left. If I let this go for 2 half-lives, how many grams are left after 2 half-lives? I literally have the equation 100 grams, which is my original amount, 1/2 to the second power. So that's the same thing as saying 1/2 times 1/2, and I would cut that amount in half again. So 1/2 times 1/4, and I get 25 grams left. For it to go through 2 half-lives, it would take 11,460 years for me to go from 100 grams to 25 grams. If I went through a third half-life, you could probably guess I would just cut this number in half and I would end up with 12.5 grams. And after 17,190 years, that'd be 3 half-lives, I would have the 12.5 grams. If I went through another one, 22,920 years, so I've gone through 4 half-lives, I would end up with 6.25 grams left. So you can see how long it takes these samples to actually disappear and go away. So these next slides are just practice problems. And I'm not going to take you through these right now because I have an educreations video you're going to watch. It's going to do that in just a second. So this is a practice problem. This is a practice problem. This is another practice problem. And problem 3, 4, and 5 on here are other practice problems. We're going to do these in class. I've done some of them for you on the educreations video, but what I want you to do is make sure that you leave plenty of room for us to go through these in class. You're getting the gist of the notes, and then we're gonna go through this together and explain how this process works, and you should hopefully by the end of it understand how to do a half-life problem. So I'm gonna take you back to the educreations video here in just a second, but before class I want you to watch the screencast. I want you to write out the notes that I've told you to write out for Objective 6. You're going to take the short quiz on Edmodo and answer the discussion questions. In class, there's a whole list of stuff that we're going to do, but you notice this is going to take 2 days. And I have marked what we're going to do on the first day. We're going to watch the video clip. You're going to work practice problems. We're going to read No Dumping Allowed and have a discussion on it. We're going to read Detecting Radon and have a discussion. We're going to do half-life practice problems. We're going to do a half-life candy lab. And then the second day, we're going to do a reading on carbon dating. We're going to play a radioactive dating game. We're going to develop a test question related to half-life. We're going to do this particular reading, and then I'm going to have you guys do your summary template and then work on your vocab sheet, as well as finish up any half-life practice problems that you might need to do from the day before. So I'm going to go ahead and flip over to the educreations video, and I'm just going to let that finish the screencast because that takes you through some example problems. So for the rest of this video, this is what you guys are going to watch, is just me solving some half-life problems for you. Problems using the half-life equation. Before I get started, I want to explain to you really quick the half-life equation. So A equals AO, and then 1/2 times to the T over H exponent. So what each of these things mean is this is what we're generally going to be solving for. That's the amount that's left. This is going to be the amount that you start with. And you are going to take that times 1/2, whatever the amount of time you have over the actual half-life. In all of these problems, this exponent is going to be a whole number. You're going to see that. So we're going to have 1/2 to the second, or 1/2 to the third, 1/2 to the fourth. These really aren't that hard to do once you just understand the basic format. So the sample problem that's in your notes, I worked through with you during the screencast. Problem number 1, I'm going to work through this just so you can see where these numbers came from. So it says the half-life of zinc 71 is 2.4 minutes. So that's my H. If one had 10 grams at the beginning, if I had 10 grams, that is going to be my AO. That's my initial sample. And I want to know how many grams would be left, so I'm going to solve for A. I want to know how many grams would be left after 7.2 minutes. So that's my time. So when I plug this into my equation, I get A equals 10 grams times 1/2. And then my exponent is going to be the 7.2 minutes, which is the time, over the half-life. So 7.2 over 2.4 minutes. When I take 7.2 divided by 2.4, I get 3. So I have A equals 10 grams times 1/2 to the third power. So what you have to do is plug this into your calculator by putting in what I did. The easiest way to do it is just do 0.5 to the third power and then hit enter. And then you're going to take that times 10, and your answer that you get out of your calculator is actually 1.25 grams. But you have to go back and look at sig figs. This number has 2, this number has 2, this number has 2. So you can only have 2 in your answer, so A equals 1.3 grams. And that's where you get that number at. 1/2 to the third power is the same thing as taking 1/2 times 1/2 times 1/2. And when you do this right here, 1/2 times 1/2 times 1/2, that equals 1/8. And that's where the 1/8 comes from. So I'm going to do another example problem for you. So that was problem number 1, in your notes. I'm going to do problem number 2. This is the one that says, this is the one that says problem number 2. And next to it says we. So we have palladium 100, so Pa 100, that's my isotope that I'm working with. It has a half-life of 5 days. So it only takes 5 days for the sample to cut in half. So 5.00 days, that's my H. If one had 6.02 times 10 to the 23rd atoms to start with, how many atoms would be present? So that's my AO. How many atoms would be present after 20 days? So 20.0 days is my time. So I'm still solving for A here. And I literally just have to plug in what I have. So A equals 6.02 times 10 to the 23rd times 1/2. And then that exponent is going to be 20.0 days divided by 5.0 days, because it's going to be the time over the half-life. Well, 20 divided by 5 is 4. So this is the same thing as me saying A equals 6.02 times 10 to the 23rd times 1/2 to the 4th power. That's the same thing as saying 1/2 times 1/2 times 1/2 times 1/2. And if you do 1/2 times 1/2 times 1/2 times 1/2, you end up with 1/16. So that and 1/16 are the same number. So now to solve for it, I just take A equals 6.02 times 10 to the 23rd, in parentheses, times 1/16. And when you plug that into your calculator, you get 3.76 times 10 to the 22nd atoms. So that's how many atoms would be left over in this sample after 20 days. If I started with this amount after 20 days and that half-life, this is what I'm going to have left. So go back and look at your sig figs. This number has 3, this one has 3, this one has 3. So my answer, of course, can have 3, and I'm good to go. I'm going to work through one more problem with you. I'm going to do problem number 3, which is on the next slide. It's the one that says 2. You can go ahead and write this one down in your notes, and then you can do problem 4 if you want to. You can do problem 5 if you want to. That's part of your notes. But I'm going to go ahead and work through problem 3 with you. So it says osmium 182. So I have osmium 182. It has a half-life of 21.5 hours. How many grams of a 10-gram sample, so 10 grams is my AO, how many grams of a 10-gram sample would have decayed after 64.5 hours? So my time is 64.5 hours. So as I set this equation up, I have A equals 10.0 grams, because that's my AO, times 1/2. And I'm going to have time divided by the half-life for my exponent. So 64.5 divided by a half-life of 21.5. So when you take 64.5 divided by 21.5, you get 3. So A equals 10.0 grams times 1/2 to the 3rd power, because that's 3 half-lives that I have to go through. Taking 1/2 times 1/2 times 1/2, which equals, and I get out of 3, and that number has 3, so my answer can have 3. And that's how many grams would remain after 3 half-lives of this sample with a half-life of 21.5 hours, and I've only given it 64.5 hours. So this is just a way to determine how much sample